Hello, my name is Leo Micklem from the University of Southampton, and today I will be discussing our paper on energy-efficient tunable stiffness soft robots using second moment of area actuation. My area of interest is the subsea potential of soft robots. We've already seen much progress in the area, with examples here of fish-like robots and jet propulsion robots, and a soft robot at the bottom of the Mariana Trench. We are still looking for a solution that gives us a high efficiency range with comparable maneuverability to existing rigid solutions while staying soft. But the potential is there. To unlock this potential, many pieces of the puzzle are already in place. We already have soft, flexible systems that can produce large amplitude deformations. Flexibility, which allows large amplitude deformations, is important for swimming. One reason is that it allows swimmers to leverage resonance. Objects and systems deform most easily at resonance, which maximizes the amount of energy that is used for useful work. In other words, the amplitude gain is maximized. Some jellyfish save 30% of their energy costs by swimming at resonance. We also have open loop on-off control, allowing us to switch between two stiffness states. For example, the NASA re-entry heat shields inflate to 2 bar pressure with no atmosphere. And there are flexible strain sensors, which could be used for feedback control. The missing piece of the puzzle is efficient and continuous tunable stiffness. If we have efficient and continuous tunable stiffness, it is possible to have soft control surfaces for truly soft robots, with maneuverability as good or better than AutoSub. This tunable stiffness will also allow for an expanded range of efficient swimming speeds. For example, Bouchard's jet propulsion robot only has one resonant frequency, at which it is very efficient, but past this frequency, it becomes inefficient. If we have a range of stiffnesses, such as low, medium, and high here, we could improve the efficient operational envelope of frequencies. Currently, there are no simple mechanical approaches for effectively and continuously adjusting stiffness. For example, this thermal gripper gives a range of stiffnesses, but is a slow process with a high energy cost. We propose a new soft method for tunable stiffness by inflating rubber tubes to geometrically increase stiffness. We put the tubes in a silicone housing connected to a rigid nose, which houses the pressure tubing. Our aim was to create a soft method to increase the operational envelope of high efficiency frequencies. So how does it work? We model the tubes as an inflatable cantilever beam, for example, with a point load. If the tube is inextensible, we can experimentally and theoretically predict the collapse loads. It can be seen that there is a max pressure stiffness, and that increasing the pressure only delays the onset of buckling. Pre-buckling, it is just governed by normal beam theory. Pressure has no effect, only on when buckling occurs, which makes it dangerous and difficult to use as a control variable. But what if we had a flexible tube? With a flexible tube, the increase in pressure increases the second moment of area, which allows for the continuous control of stiffness. As you can see here from this simple test, two tubes are equally loaded with the same internal pressure, but the far tube, which is allowed to expand, is deflecting less and therefore stiffer than the inextensible tube. To test this as a control surface, we carried out a variation of the classic three-point bend test. The nose is attached to a rotating bar where we apply moments, and the tail sits on a rotating bar. We apply an offset moment to remove the effect of mass of the system. The arm measures rotation, which can be used to find the deformation A, and we apply a moment, which gives us the applied force. We can rearrange this to give us an effective stiffness. We carry this test out for a range of pressures and loads and plot the results here. There's a clear increase in effective stiffness with pressure, and we double the effective stiffness for 0.8 bar pressure change, which is just 2 joules of energy, 5 to 6 orders of magnitude less than the thermal gripper we saw earlier. and all the intermediary states are attainable. Thus, we have a control surface. We also tested the system dynamically using a fixed amplitude frequency sweep with a 6-degree peak-to-peak amplitude. We tested from 1 Hz to the max frequency that was achievable with our system, and as you can see in these GIFs, that approaching resonance gives us a bigger amplitude gain. Both of them are at 0 bar. Here we plot the results. We have the measured amplitude normalized by the 1 Hz amplitude against frequency. And you can see that we have an amplitude gain of more than 5 over a 1.5 Hz frequency range, which triples the range if we only had one stiffness. And so, comparing, we have shown that we have an increase in the operational envelope as we predicted. Thus, we've completed the puzzle. We have a feasible approach for tunable soft control surfaces and propulsive fins for a new generation of soft robots. Now that we have the pieces, the next challenge is designing systems that integrate them all together. We've since made a start at looking at underwater applications. We've conducted our next set of experiments underwater. We've repeated the frequency sweep experiments in a flow channel where we measured the forces on the system and also took PIV images of the flow structures and foil deformations, and we are currently processing these results for use as a swimming robot. Thank you for listening. I'll take any questions you may have.